All right, we're recording. John's not here. He's out of town. Josh isn't here, but I'm guessing he might be here late. Okay, so here we go. Do y'all have the correct page for the lab on there? All right, we're going to be looking at some very general stuff about analyzing and interpreting experiments. So we need to understand this word, an experimental variable. Is that right there for you? Write that down and put a star by it. It is an aspect of an experiment that changes during the course of the experiment. Okay, an aspect of the experiment that changes. So if I'm asking a question about something, John, Mark?
Oh, I was going to ask something about I was going to say something about the experiment.
Okay, go ahead.
You can carry on.
What?
You can carry on.
Carry on. All right. So if I'm asking a question about something, and I'm going to make a right, I think something will happen, right? Whatever I think will happen, and then we have to test it. It's always good to have something next to it that didn't get tested, so we know what it acts like normally. John Mark.
Like an experimental variable is like a different turn of events, you know?
Yeah.
Like this small part could change a whole lot of this, you know? Like the
It's something. It's actually the thing we're testing.
yeah.
It's what we're testing, and that changes. Does everybody understand what I'm saying? We'll I'm going to watch a video right here real quick, and in fact, our definition will still be up there, so if you're still writing, you have time.
If you really want to learn something from a scientific experiment, you have to be sure to control your variables. The scientists in this video, for example, are doing experiments with chemicals that are similar to some of the chemicals you can find in the human body. Now, if they were to contaminate their experiment with chemicals from their own body, that would introduce unwanted experimental variables. As a result, they're covered up in clothing and wearing masks to prevent that from happening. Many scientific instruments control experimental variables as well. This one controls temperature, pressure, and other things so that the only true variable is the one the experimenter wants to analyze.
Okay, so a variable is something, to vary something means to change it, all right? So it's something we're going to change, and then we want to make sure we don't have any unintentional ones, unintentional variables, like the chemicals or whatever they were talking about on these experiments right here. All right, so I don't know if this is a clumsy way of saying it, an aspect, you could say a thing, the part of the experiment that changes if you don't want to use that word, if that word gives you fits or whatever. All right, so we have to therefore design our experiments carefully. For instance, if we are going to see if, let's say we're going to test a fertilizer to see if the fertilizer is really good. What we're going to do is we're going to plant some plants, and we're going to put fertilizer, soil, and water, and let sunlight here. But we're going to also keep a set of plants, same area, with all the same conditions except the fertilizer. Okay? So because I could say, what if I just grew a bunch of and they grew really well? I said, that fertilizer worked great. Well, do we know the fertilizer worked great? Not really, unless we have something next to it that didn't use fertilizer and it grew really crummy, and the fertilizer ones grew really well. Then I have something to compare it to. So that's called a control group, okay? We want to avoid flaws by predicting variables and controlling them, all right? So we have a control group. For instance, what if I had my group of plants that were considered my control in 2 counties away? Would that really count? What might be different 2 counties away? Would they maybe get different rainfall? Maybe the temperature's a little different? So I need to have them side by side. That's a variable I don't want to change. I don't want to have a variable there. The only variable I want to have is going to be my fertilizer in this particular experiment, okay? Which brings me to the science fair. Okay, so if y'all are interested in doing a science fair project, boy howdy, will you get some extra credit for that, okay? And what it is we set up a fair, and you can actually present it to class. There it is. Josh, you're going to need to stay after class to take your quiz. Okay. My other class will be in here at the time, so sorry about that.
I didn't hear any class, sir.
Do y'all need to push that table a little bit for Josh to fit in? There you go. All right. So we typically, the science fair is held in January. ODA is really very, very interested in still holding a science fair, but of course with the COVID situation, we're having a little difficulty. And one of the things we can do to change it, to make it more possible, is to maybe move it later. Instead of January, maybe have it in March or something when things have started to really calm down, we hope, okay? But you can also present it to class and get extra credit for it. If you go to the science fair, you would end up taking it to Austin, and you get a ribbon and all this kind of stuff. I wanted to give you a few ideas of what would somebody do for a science fair project. So this young lady here has a question. Does candle color influence burn rate? She wondered, do some colored candles burn more quickly than other colored candles? And so I thought, okay, that's an interesting question. And so what is she going to do? She's going to set up her candles, and then of course she's going to probably, what do you think she's going to do as far as lighting the candles? Look, how many does she have? 1, 2, 3, 4, 5, 6, 7, 8, 9 or 10, and it looks like there are 2 of each. Yeah, so how would you conduct this experiment? What would you do?
Light all of them.
Okay, now, could there be a problem with lighting all of them? Olivia?
You'd have to light them all at the exact same time.
You would, yeah. So unless you have 10 people who all go ready, set, go, and we all light our match at the same time, so there might be a variable that we're not controlling very well right there as far as getting them lit at the same time. What would be another option? David?
How far down they burn.
Okay, yeah. I would guess that eventually they would all burn down to the bottom, wouldn't they?
Yeah.
Unless they're crummy. Anything else? What other ideas might you have? Okay, how about lighting them one at a time and timing it? How about that?
Yeah.
Would that be a little more controlling
Yeah.
of it? Also, what about the time, and then you burn them down to a certain level, like you measure a level on the candle, and you measure, and how long did it take to get down to that level? Not all the way to the bottom because maybe it's stuck in the wax is melted, something like that, you know, so you have to think about those things. So what did she do? She asked her question, and then she made a hypothesis. So she said, I think, and let's say her hypothesis was color doesn't influence the way a candle burns. She could have done it that way. Or maybe she had this question because she noticed on her birthday cake that those red candles seemed to really be going quickly where the blue ones didn't. Maybe that's why she came up with the question, I don't know. Typically, when you pick a science fair project, you need to pick something that you're interested in. Okay, something you're interested in, not something boring. You know, so I was watching a little video about a guy who was coming up with ideas for science fair projects, and he said, whatever, it was an adult, a teacher, saying, whatever you do, don't make your students do that plants growing in the dark and the sunlight one. And I'm like, oh. He said, that's really boring. You know, but think about it. Put a plant in the sunlight, it's going to grow. Put a plant in the dark, it's not going to grow, right? So our difference would be sunlight. So I guess it's obvious, and maybe that's what makes it boring in his mind. Okay, what about this guy? We eat nails for breakfast. We eat nails for breakfast. Okay? So what he wanted to do, he wanted to figure out which cereal has the most iron in it. All right? And so remember we looked at the sides of packaging, and the packaging would have told, we didn't talk about that, did we? On everything you eat, there's packaging information that tells you what's in it. And if you look, does anybody eat cereal? Yeah, look at your cereal box, and it's probably been fortified with iron. They probably added iron to it, and that's so you can have it because it's a nutrient that you need to keep you strong. It keeps your blood nice and strong. And so what you do is you take these and you actually, it's kind of gross, you blend them up with some water, then you run it through like a little tube, like a old bottle of water bottle or something like that. And as you run it through, you keep a magnet around it, and the magnet will actually pick up the iron that's in there. And then he could have measured the amount of iron that he found in each one of these to see, you know, which one of the cereals had the most iron. Here's one called Can Temperature Affect the Strength of Rubber Bands? Huh. All right, so maybe you have this same kind of rubber bands. Some you would put in a warm place, some you would put in the freezer, and then you would check the strength of them by seeing how far you could stretch them, and that kind of thing. All right, so when it comes to our variables, we have these things called independent and dependent variables. So the factor that's being changed is known as the independent variable. We're calling that a variable. Okay, so don't worry about the word independent right there. It's something we manipulate. It's something we change. I changed the independent variable. The factor that's measured or observed is called the dependent variable. What did it do? So I'm going to give you an example. There's a guy running on a track, all right, and we have a question. Which shoes will be faster on the track? Okay, so which shoes are best for running on this track? And we're doing speed at this point. Okay, so he has some tennis shoes, and he has some hiking boots, and he has men's dress shoes. All right, so what would your hypothesis be? I think, Josh?
I've tried to run in dress shoes before
It's
because
not-
I was rushing and I fell over.
Oh, really?
So
And
yeah.
it might like leave blisters on your feet, you know, because they're kind of stiff shoes, right? So my hypothesis would be, I think the running shoes would be the best shoes for the running track, right? Doesn't that make sense? David?
I think the running shoes, but the problem is, you see that if you do different people, they might
Oh yeah.
be faster than each other.
Yep.
If you do the same person, he might be worn out on the second one and more worn out on the third one.
All right, so you're coming up with some good variables here that we might. So we're trying to make our variable be the shoes. Yes?
Yes.
But there's other variables. We can't do two different people because they're just way too different in the way they run, unless we're doing 3 Olympic runners or something, right? So, and then the other one is getting tired out, definitely. And so, how could we design the experiment around that problem, Olivia?
You could do it like over 3 days. So the first
Good.
day you run with the boots, the second day you run with the dress shoes, and then the third you run with the like running shoes.
Right. So we could do something like that. We'd also try to do it at the same time every day, hopefully the same weather conditions every day. You know, maybe do it at a time of the year where the weather tends to be the same. And why would that make a difference? On a day like today, doesn't everything, the air just seem so heavy, right? It seems just heavy out there. That's because we have moisture, a lot of moisture in the air, but we have lower atmospheric pressure on a day like today. That's how the clouds form. If we have high atmospheric pressure, it kind of moves the clouds right on out there. So that'd be a sunny, bright day. Okay, so we start our timer, right? And our timer's going to go, and then we're going to, having taken all those things into account, we're going to test this. Now, I have one more question for you. What about psychology? Do you think the runner might, in his mind, have an idea of which shoe is better? Right? He might say, well, obviously the running shoe's going to be better. And do you think maybe he might just perform better with that? Do you think psychology plays a part? Whenever you're working with human beings, psychology will play a part. Next week, we're going to look at that and how profound that can be sometimes. Okay? There are people sometimes who take a fake pill and it makes them feel better because of psychology. Yeah. So our mind's a powerful thing. All right. So those are our variables. And we're going to do a little lab today with variables. But I'm going to get prepared. We're going to be preparing now for our water lab, which will be next week. The lab will be next week. But we're going to start talking about water this week. So you can see there's water on this stem of a plant right there. And we might call that a bead of water, right? Bead of water. It's fixing to drop. Do you think it's fixing to drop down? Like a raindrop? Yeah. So it turns out that water is a very interesting liquid. It's a miracle liquid, and it's the stuff of life. Without water and the way that water acts, we would not have life as we know it on this planet. We would not have life as we know it in our bodies. Okay, so we're utterly and completely dependent upon water and how water acts. And one of the things it does is it's sticky. It sounds weird to think that water is sticky, since we think of lollipops and things as sticky and we wash it away with water. But what water is sticky toward is itself. Water sticks to itself, okay, because it's very specialized. It has H2O, it has 2 hydrogens and an oxygen, and those tend to form a very partial charge, electrical charge. I almost said magnetic charge. It's kind of like magnetic, but it's electrical, and electricity and magnetism are related to each other. And so what happens is that each one of them are attracted to the other ones, and if I leave them completely alone, like right here, they will form a drop like this because they're going to glom around each other, okay? Now, we live on a planet that has gravity, and so it's rare that, like when this drop happens, it happens so quickly that we really can't see it, right? We can't see it happening, but a picture can capture it. The guys up in the space shuttle, now we don't have a space shuttle anymore. Okay, what do we have? The International Space Station, the guys who are in space. You know what happens to water when you Drop it in space.
It floats.
Yeah, but what does it look like?
It looks like food.
Like what?
Like food falling. It's
It
like-
doesn't fall.
It kind of just floats around.
But it's a complete sphere, like this. It's a complete sphere, because it's just round. And those guys have to go. They'll take a straw and sip it up and drink it, you know. And this, cause they can't let that water droplets be flowing around these. It's like you're living on a computer, and so if it hits your computer, it could damage them. And so, but when left alone, it's going to form a sphere like that. Okay, but since we're on the Earth and we have gravity, it's going to pull it down. Okay, but it still has this property. This property is known as cohesion. Have you ever heard like, oh, we're a very cohesive group? If we're a group of people that are cohesive, that means we're sticking together. Okay, and we're doing this project together. That's what water is. It's cohesive. So it has cohesion. It also has tension. All right, so water tension. So you can see right here, there's a bug, and it's standing on the water. Can we do that?
No.
How much Jesus?
Some people call this the Jesus bug, all right? But it's called a water strider. There's another name for it. I can't remember it right now. Also, have you ever tried to float a paper clip on a cup of water?
No.
Okay, we're going to do that next week. Okay, we're going to try that and see how well we do, all right? You can do it because of surface tension, not because of the paper clip, but because of surface tension. I was going to do this today, except I didn't have any paper clips. I had some of the really big ones, and I could never get it to float, so I was worried that it may be because it was the big one. I don't know, maybe I should have given y'all that challenge to do that. So I have to go get some regular size paper clips. I use them all for this class, and when they get wet, then they get rusty, and I have to throw them away. So, all right, so once again, you're seeing how the water drops are cohesing to each other. All right, so when it gets to the surface of the water, so right here on the surface, what happens is they can't form that circle like that. They're all forming that circle like bubbles almost underneath there. But at the top, everything gets pulled away this way, and there's a force at the surface. Okay, and so we call it surface tension. And water's really good at it. And you've noticed that if you've jumped off a cliff into the water, not a very high cliff, y'all. You know, a cliff you're supposed to jump off. If you jump off of even a diving board, if you jump off of a high dive board, and if you hit the water in a belly flop, how does that feel? Ouch. That's because it's like you're hitting the surface tension of that water. It's really like hitting something solid. All right. Now, when the Olympics come around again, weren't they supposed to be this past summer, and we got canceled? I think it was in Japan. When they have the Summer Olympics, watch the high divers. They're up on the giant diving board, even the low diving board. You're going to see the pool, and there's a little fountain that sprays into the pool. And you know what the fountain is doing? It's breaking the tension on the surface of the water. That's why they do it, so it doesn't hurt so much if those guys have a belly flop. I don't know if Olympians would end up with a belly flop. I hope not. They wouldn't get a very good score. Josh.
That's why a lot of people like put their hands in like this or like
Absolutely.
make their toes like
Right. So that's why going in straight, you're going to have less area of that tension area that you're going to be hitting. John Mark?
Why wouldn't you?
I can't understand you.
Why wouldn't you?
Get a good score?
No, just why wouldn't you do it?
Jump in the water?
Belly flop.
Oh, belly flop. I'm not going to belly. I won't even jump off a cliff. My kids like to jump off those cliffs at Lake Travis. I'm not going to do that. I think there might be a rock, not to mention hard water, hard rock under there. So I'm not going to do it. But that's why this happens this way. Let's watch a little video about these water striders. He may tell us the other name of it.
The water strider, also known as the pond skater,
Pond
is an
skater.
interesting insect. It lives on the surface of streams, lakes, rivers, and ponds, and it actually walks on water. How does it accomplish this task? Well, it uses the surface tension of water. Just like the needle was able to float in your experiment because of surface tension, the water strider is able to walk on water because of surface tension. If we zoom in on one of these insects, we'll see that surface tension in action. Like all insects, the water strider has 6 legs. Notice what happens when those 6 legs touch the water. They form dimples in the water. Those dimples are the result of surface tension. The weight of the water strider pushes down on the water. However, the water molecules want to stay together, so the surface of the water has tension. That tension pushes up against the water strider, and the water strider doesn't sink. When the water strider wants to move, it simply pushes against those dimples. Surface tension pushes back, and as a result, the water strider is propelled forward. That's how the water strider walks on water.
Okay, I'm gonna go back for a second. So do you see how there's a little dimple formed around that paperclip? Yeah, it's almost like it's bending it in, like a little, like on a sheet or something like that. So when we try that next week, we will see that. Okay, now we're going to talk about graphing, because we're going to try to do some graphing today with some of the data that we collect from our experiment. So you can look at these graphs right here, and you can tell me something right off the bat. It doesn't tell us what's going on, right? But you can tell whatever's happening, it's going up, right? It's going up. So this one started at 5, and it went up to 7.5, all the way up to 8 something, 8.2 or so. This one also went up. All right, we have years down here. That tells us, tells us maybe inches. This is not very well documented here, because that should tell me more like units. It should say inches or feet or whatever it is that we're measuring. All right, so each one of these squares here and dots here are a data point. So when you do an experiment, you can collect data and get a data point. Now the experiment we're going to do today, using the graph for it is not the greatest, but we'll have to do it anyway. So we're going to watch this little video. It goes on for a little while, so don't fall asleep, okay? Pay attention. But he's talking about something about amount of dissolved oxygen in something, and then depth in meters, okay? So pay attention how he puts the data points on and then connects them.
In case you're having trouble understanding the graph and the figure, I want to show you how it is put together. Let's assume that the blue area in this drawing represents the Bering Sea. And what I would like to do is develop a graph that shows how the amount of dissolved oxygen changes with depth. First, let's understand the graph itself. If I want to show how the amount of oxygen varies with depth, I've got to show both oxygen and depth on the graph. I do this by using two different axes. The first axis, which we call the x-axis, is the one that lies horizontal on the graph. This axis represents the depth. The farther you go to the right on the x-axis, the deeper you are in the Bering Sea. The other axis is called the y-axis, and it runs vertically on the graph. It represents the amount of dissolved oxygen. The higher you go on this axis, the more oxygen is dissolved. All right, now that we understand the graph, we need to measure the amount of oxygen in the sea at different depths. To do that, I'll use my little oxometer, which is shown there on the left. As that goes into the water, it will measure the amount of dissolved oxygen that's in the water. All right, now let's measure the amount of dissolved oxygen at a given depth. We'll start at, say, 200 meters. We put our oxometer down there at 200 meters, and it has a reading of 0.55%. So the amount of dissolved oxygen at a depth of 200 meters is 0.55%. Now, how do we represent that on the graph? Well, first I'm at a depth of 200 meters. So let's look on the x-axis. Remember, the x-axis denotes depth. And let's find 200 meters. Think about what that means. That's the distance to the right on the graph that represents 200 meters. So any point that's that far to the right on the graph represents a depth of 200 meters. At that depth, the oxometer tells us that the amount of dissolved oxygen is 0.55%. So let's find 0.55% on the y-axis, which represents the amount of dissolved oxygen. Now, 0.55 is not actually listed on the y-axis, but you can figure out where it is. What you have listed on the y-axis is 0.5 and 0.6. 0.55 is halfway in between the two. So the point halfway in between 0.5 and 0.6 on the y-axis would represent 0.55. Now look what happens. I have two red lines, one representing a depth of 200 meters and the other representing a dissolved oxygen percentage of 0.55. Notice where they intersect. They intersect at one point. That's the point that represents a depth of 200 meters and a dissolved oxygen of 0.55%. So that's where we put our point on the graph.
Data point.
We now have a single point on our graph. That point tells us that at 200 meters, the amount of dissolved oxygen is 0.55%. Now let's move to a new depth, let's say 400 meters. When we bring the oxometer down to 400 meters, we notice that the dissolved oxygen goes up. It is now 0.60%. Well, once again, I can find 400 meters on the x-axis, and I can find 0.6 on the y-axis. When I find those two numbers, they intersect at one place, and that's where I put a point. And that point tells me that at a depth of 400 meters, the amount of dissolved oxygen is 0.6%. Now, let's suppose we want to be a little more detailed. We know the amount of oxygen at 200 and 400 meters, but let's suppose we want to track the oxygen in smaller intervals, say depths of 50 meters. Well, to do that, we're going to have to go back and start at 50 meters and figure out what the amount of oxygen is there. When we put our oxometer at a depth of 50 meters, it reads 0.60%. So, we need to find 50 meters on the graph. Where is 50 meters? Well, it's about a quarter way between 0 and 200 meters. So that's where we find 50 meters on the x-axis. On the y-axis, we find 0.6. Those intersect at one point, and that's where we put our point that represents 50 meters. So we now know that at a depth of 50 meters, the dissolved oxygen is 0.6%. Okay, now we continue, but in increments of 50 meters rather than 200. So the next depth would be 100 meters. At 100 meters, the amount of dissolved oxygen is 0.70%. 100 meters is halfway between 0 and 200, so we find that on the x-axis, we find 0.7% on the y-axis, and we put a point there. Next, we go to 150 meters. At 150 meters, the reading is 0.60%, so we find 150 meters on the x-axis, that's about 3/4 of the way between 0 and 200, and we find 0.6% on the y-axis, and we put our point there. We already measured 200 meters, so we don't have to do that again. So the next depth is 250 meters. When we go there, we find that the amount of dissolved oxygen is 0.50%. So we find 250 meters on the x-axis and 0.5% on the y-axis, and we put our point there. The next depth is 300 meters, and we find that the dissolved oxygen there is 0.45%. So we find 300 meters on the x-axis, 0.45% on the y-axis, and we make our point. Then we go to 350 meters. At 350 meters, the amount of dissolved oxygen is 0.50%, so we find 350 on the x-axis, 0.5% on the y-axis, and we make our point there. Now once again, we've already done 400 meters, so we don't have to do that again. If we were to continue the process all the way down, we would end up getting the graph you see in your book. What does this graph tell us? Well, look at the dots, and remember that the farther right you go in the graph, the deeper you're going in the sea. What the graph tells us then is at shallow depths, near the left part of the graph, the amount of dissolved oxygen goes up, down, back up again, and then down again. However, when it reaches about 500 meters, the amount of dissolved oxygen has gone down to about 0.1%. After that, it starts a slow but steady increase. The deeper you go, the more dissolved oxygen you find in the water. That's what the graph tells us.
All right. Woo. Took a while, right? Okay, so we are going to try our experiment now. Did you have any blanks that didn't get filled in? We're all good, right? So our experiment is going to be our egg in the water. Okay. So can y'all take some goggles and pass this around, please? I don't know that really we need goggles today, but you know, never. So we're gonna try this. What we're gonna do is we're gonna start with an egg, and it's gonna go into a beaker of water, and then we're gonna have a variable. But we want to control our variables. So let's talk about it. I'm gonna bring around to you a couple things. Okay. So each table is gonna work with this. So everybody's gonna get a beaker. Large or small? Any preference? Okay, so you're starting with a beaker. That's one of the things if you want to. Do you have a lab sheet? Okay, you know on page, what page is that? 17. We're going to use this data on page 17. We're not going to use the lab report on page 19. We're going to save that for next week. Okay, so does it ask you what you have, materials you have? Okay, here's the question on the floating egg. How many spoonfuls of salt will it take before my egg floats? Yeah, write that at that top. And then you have your hypothesis, so your introduction, that's your introduction, how many spoonfuls, and that is the proper grammar, it's supposed to be spoonsful, but it's spoonful, of salt will it take before my egg floats? Yes.
Can I just see?
What?
There's no one.
Alright, I'm ready.
Okay.
Miss Casper,
Yes.
can I switch these are
Scratched up or dirty?
they're all dirty.
They're older ones.
I'm
The
ready.
ones with the bold picture on the newer ones. I'll put these over in this.
They stay up.
Safety first. How many spoonfuls of salt?
Yes. Will make my egg float. So here's the other things you're gonna have. You're gonna have a cup full of salt, a beaker full of water, 2 spoons, and an egg.
I could have never guessed the egg.
Yeah, that was a tough one.
We did that one.
Last week too. Yeah, last week. Egg was our thing. Yeah, it's classic.
Okay. Are you gonna put the entire cup of salt?
No.
Why? You're so way too low.
Salt's at my house all plenty and hers is just like.
Well, it's probably pretty new.
What's it smell
It
like?
gets clumpy at my house too because it's all salt.
Salt.
Smell like the ocean?
Yeah, you end up eating more salt than no.
Salt doesn't even smell like it.
If you put water in there, it'll probably smell like the ocean.
Is there gonna be like a trick egg or something?
Trick
The
egg.
ocean has a smell. What are you talking about?
Hard boiled egg.
No.
Of course the ocean has a
Take
smell.
like a rotten egg, something that.
No, no
Because
rub.
it has salt.
One that's already
so
very
obvious.
One that's already.
Oh, here's your egg.
But the salt is to give, keep your hand on that beaker.
Fried eggs and a piece of toast.
That's your puppy.
Can I use your
Bucket.
Freaking-
Bucket.
Isn't that your fire truck?
What if I
Yeah,
did
gas
that?
Bucket.
I think that's like.
I'd like take my test and go take it in there.
What if I
It's like, I'm used so mad at you. I go like this. Only for a million. No, I
One time I was drinking some Dr. Pepper. My
Oh,
mom
oh,
made me
you're
laugh.
like,
One time I was drinking Dr. Pepper, my mom made me laugh. It's what it just came out of my nose. It burned so bad.
oh yeah, that's
Alright.
Okay, I'm gonna bring you an egg, okay? And you're gonna carefully put it into your beaker. And it should sink. If it doesn't sink, we're cooked.
We're cooked. Literally.
It feels like everything's
Egg.
So,
Can I have
you
an
may
extra one so I
want
can go to
to,
her?
listen up, you may wanna lower your egg carefully into your beaker with a spoon, but make sure one of your spoons never gets wet. The other, put one spoon in your salt, cup. It's gonna be your salt spoon. Never will it get wet, you understand? Okay. Don't drop the egg into it, we don't want it
Oh
cracked.
my gosh. Another ambulance in this house.
So none of our spoons can get wet.
Right, let me get wet. Do we do it right now? I'll figure out how you're gonna work your deal. Now, nobody do anything until I tell you. You may go ahead and put your egg in your water.
That's a dump. That was like. That's like.
And hopefully it's gonna sink to the bottom.
It's not.
Are they sitting on the bottom of the beaker?
Yes.
It's so big.
It looks like
Why is there hair in there? Look, there's hair.
It's
That's your hair. Is that your hair?
No, it wasn't there.
Well, All right, now listen, y'all.
Put it down here like
We're gonna have a variable here, right? We're gonna change something. What are we gonna change?
I wanna eat. With the normal food.
What's the thing? What's our variable?
Water.
The egg, the water. No, it's gonna stay the same every single time. What's gonna change?
The float, the high.
Wait, no, that's the dependent. That's what's going to happen when I change something. What am I changing?
Changing the water.
Oh my.
What's my variable?
No more distributing.
The water.
No.
The salt.
The salt.
That's all. I just said that. I said
Oh,
that.
wait.
I said salt.
I heard that was out. All right. So now here's a couple things you have to decide among your teams here. Okay. So you have to figure out who's going to do the salt. Don't you think the same person has to do it every time? And so look at the salt on the spoon and see how big of a spoonful. If you want to like top it off at the very top and do your finger across it, whatever you do it the same way every time. All right, so we have equal spoonfuls. You understand? We don't want that variable to get in there. Now, what if I'm coming over, like what if I have the cup over here and I get my spoon and I say, okay, it's gonna be that much each time, and then I can start to go over here and I bump and I spill some on the table.
You start over.
You have to, right? Because that was an unaccounted for variable. I dropped
Look,
something.
you do.
What if I drop it in so violently that water splashes out of my beaker?
Then
Look.
start over.
Yeah, well, I mean, it's hard to start over then, right? So
Yeah.
you can't, don't do that is what I'm saying, okay? Now,
Like-
here's the next question for you. Since you have a second spoon, when you put the salt in there, do you wanna then stir
I will
the
stir.
salt up? If you do it the same exact way every single time, you understand? And then, of course, one of you needs to be keeping track. Well, actually, you're gonna write it down in your book. When I put in 1 spoonful, so I think this is a little awkward in your book right here. It says, did the egg sink? Well, the egg is, so it's gonna be yes, 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 yes. I think it should say, don't you think it should say, did the egg float?
Yes.
I tried to tell the people in charge to change that to the word float, and they didn't listen to me.
Right
So you can either scratch that out and say float, or sink and you're going yes, 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 no, or
What?
float, no, 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 yes. Do you understand? Okay, so it's up to you. Alright, so you, in your team, you make a decision. What size of salt are you going to stir,
I'm gonna.
etc. Okay? And then you can get going. Wait, before you start anything, you're gonna make a guess. What do you think's gonna take? It's eight.
6.
6, 8. So just write that down. My hypothesis. I think it will take this many spoonfuls.
How many
of salt.
spoonfuls? I think it'll take 6.
So if you have zero idea, you're like, I don't know, I know, just guess something, guess 100, and you'll be wrong, okay, you'll be wrong at 100, so you can do that and do that on purpose, and say, oh, my hypothesis was wrong. You could guess 1, and you'll probably be wrong on there, but you never know. All right, do you think there'll be any differences between our beaker sizes and the tables? Do you think that'll be any differences? Maybe, we'll see. All right, because there's more water in those beakers in the back, would that dilute my salt more? Yeah, so y'all might get your eggs floated
Okay, you
sooner.
wanna do the
So go ahead and you can start your experiment.
Okay, so. Okay, I started eating
Yeah, that's 4. That's 4. I didn't do anything. You made me do it.
I don't. Oh, it's small. Stir it.
Hi.
Cool looking.
I was like,
What is 4? 6. I was wrong.
And y'all are not stirring, y'all decided not to stir.
Oh,
no. Well, wait, did you stir the first time?
What?
If you didn't
The
stir the
first
first
time,
time,
after each one?
no, if you didn't stir, don't stir now. That's a very
Oh,
weird.
weird.
Look, there's a drop of water. There's a drop of water on your
Oh
spoon.
my gosh.
And you're not wearing goggles. Goggles on, y'all. That's for the day.
I have my
Everyone next to me.
Brendan, delete.
Wait, what number are we on?
We're
It's
6.
on the right,
You don't have to count down?
Yes, that's not to stir. Okay, so you're good. So, okay. Now,
You're wrong.
do anything else on the card down here?
I'm gonna pour the whole.
Not floating. Okay.
Wait, what is
No,
number?
no, no,
Eight.
number. Yeah.
Brendan's
Doing it
running
5 times.
We're gonna run out.
Wow. We're
9.
gonna need more.
How many spoons have I got in there?
I already have less.
Just one? Oh, we're pretty salty.
10.
Oh,
Oh, you're gonna run out of salt.
Yeah. Yes, because he just did three.
Yeah, we said three. I was like,
Wait,
wait,
no.
three?
Three.
11.
You almost lost count.
Why?
Go ahead.
Let's go. Come on.
No, yeah, we only did this so far.
This is 4?
Put something on top.
I
Cut out some glass and fill it in, just like.
Oh my god.
Wait, how many?
That's 13.
Okay,
13.
Yeah. Oh, sorry.
You know how long it takes me?
That's 13. That's all I did. Yeah.
Sure, that's
Alright,
fine.
you need more salt back there.
I need more salt.
Oh, yeah. Hold it.
Somebody can donate me some salt.
What?
You
Hey.
wanna
told me.
Oh, yeah.
Oh, it's
Wait, what did I?
This too? It was like,
Dude.
Oh, it almost loaded and I was just touching
What was Monday though?
yeah.
What was Monday?
More salt, please.
What day?
13.
15.
Last week.
What do you mean last week?
Wait, wait, no, he's saying that it's 15.
No, it's 16.
We're on
That's 16. That's 16.
That's 7.
Your thing is floating on the salt. So yeah, but it's still touching
Yeah.
the thing. It's still touching.
Alright, I did see it try to float just now. Yeah, it was trying to.
Oh, what?
Yeah, it was trying to.
It's trying to float.
Okay, come on, put in more salt.
No, wait,
Put
do
it
it
all
with
in.
your
I'll stir.
You do it with your finger.
Oh my
Look,
god.
it's not like this.
17.
It's like
That's 17.
pour it. Pour it. It'll float.
There was a drop of water.
Wait.
Here.
Yeah.
Why? Do you want me to hold it for you?
No, I'm just kidding.
Sure, that's 8. Yes, I wrote down 7.
19.
Yes.
That's 19.
Oh no, we have a problem here. A different salt person.
It's floating.
This is 19.
Not these spoonful.
8.
Wait, what?
8. It's a cute 8, so you were right, technically.
You should have said
Well, I didn't know. I thought she would stir it.
Are you gonna eat that?
Wait.
We're the master of
This is
it.
funny.
Oh, is that
Yeah.
spoon wet?
This How did it get wet? We never even touched the water.
It never has the
We're the
water.
master of variables.
You're a mess.
Smells like sand at the bottom of the ocean.
Thanks for the support. So is yours. So is yours.
Well, ours.
Yours is way more yellow than ours is.
Like, that's wet.
Oh,
How did it even get wet?
That's what I'm saying.
or because we put it in
How many?
You know what? Give it to me.
That's 5.
Okay,
Wait, so is that floating?
I'm not a bit.
That might help.
Just stir it.
Can I just stir it now?
Yeah, go ahead. Hey, don't stir it.
What's the first thing to do?
Miss
I'm not
Casper. Can we just stir it?
Okay, then you.
Well, now that you hit your variables,
Maybe look at
I'm like, where's this?
I was one.
Is that the dry
I guess
This is the
I
sprinkle
just dried it.
What did you tell me that was? How many? You girls?
8.
Ended up with
They got it in
21.
5.
And we never.
I wonder what the
Oh,
difference
wait, hold on.
is.
Y'all probably
Maybe
put
they
more
stirred
salt.
like 5 times. We stirred 3.
How many times did you stir it?
Well, no, they'd be
How many
doing.
times you stirred?
They're at like the 20th.
We're at
counting.
21.
Maybe that was
We're
their,
at
like,
21.
How many times?
I would beat all of y'all.
21.
What was it
Oh,
about?
it's not. It's not. It's not.
Oh, wait.
Yeah, I did.
Oh, yeah, all that
Hey, we
salt.
got it. 21 scoops.
Yeah.
21 scoops.
Yeah. First.
Look, look at that.
Five times.
Stir.
Looks
That's
like
all
snow.
salt.
Looks like snow.
That was kind of gross.
Oh, look at this.
Wet.
21.
Oops, I
After you
said-
stir it, you were
After
right.
21.
I knew it was not.
Okay, but since you guys stirred, it could have floated well before 20.
Yeah.
Yeah.
So.
I mean, she got it right
Look
7
at
times.
salt.
7 times 3. She got it. Like.
Look at that.
What number?
Looks like rice.
Okay, you need more salt, John Mark?
I think
Olivia, you
so.
got it. You said 7. 7 times 3 is 21. So.
So weird. I was right.
You owe me $2.
I know.
Okay.
No. No, $3. 7 times 3. So.
I'm taking
Yeah.
Oh shoot! Let's get one more.
Oh,
The
you
last
won.
one.
Dang it, I got to stay
I
late.
want you to see, because they said 21, but they had a flawed experiment.
Miss Casper.
No.
We
I
tried our
took my
hardest.
quiz now.
We tried our best.
Yeah.
Alright, listen.
You
It's
got
not
one
our
word.
fault.
It's
We're
not-
not scientists.
It's a bubbly. Bubbly. Where
Wait,
did
it
you?
has bubbles on it.
Do you have a study
It
guide?
floats a little bit when
Oh,
I
what?
first started. Yeah.
Oh, wait.
Well, my
This thing?
Hey. You didn't know what the
Oh,
I
yeah.
know what it is.
I know it is, and you're supposed to write it up at the end, you do number one.
Okay, miss. I need to. What do I do for
Yeah. Oh, it sucks. Look, look at it.
Wait! I think I know what to I don't
You
know.
can, like.
Alright,
Can I email it to you?
Take a picture of it.
Yeah, I have to do it. Okay, I can't.
Alright, with this.
I'll just be annoying to my mom. Yeah.
So tomorrow.
Next class.
Those babies make me mad. They're so thick. And
It's just confusion.
I know, right?
That
Someone else before me. And you started.
It's one of those my size book. It was like all the way
Yeah,
down.
it's sitting up and
It
it's
was
like
like nowhere.
Thank you.
Oh, yeah, somebody on one side.
Where are y'all?
Yeah.
Hey, you can't use your book right now. Oh, look, it's trying to.
No, I'm just.
Yeah.
I'm
Do not study. You can't study during the test.
I'm not taking the test yet.
I know, study.
Oh my goodness.
I'm trying to.
No, don't study.
It's gonna be fresh in your mind.
Oh, I'm confused.
It's just
Okay.
study.
No, I really haven't.
I think I scooped while you do it on the track. Look.
Okay,
Because I have a trust here.
notice all the salt on the bottom.
I wanna eat it.
Melting snow.
Yeah, you need to hit the spoon. I do need to hit the spoon on
Okay,
here.
that'll be good.
Was last time I went to Mexico?
If you want to get
That's not
happening.
You say you want to go to Mexico?
No, I went to New Mexico.
Oh.
I go to every year, and one time I went and the snow
No,
was
that
like
is so cool.
Yeah.
I thought you said you want to go to Mexico. I was like, wait, what?
Good job, Mark.
That is very
look at the salt on the egg. Ready?
That's very
Ready?
awesome.
Full of salt. Like
Very
beautiful
awesome.
salt.
That's very
Make the
awesome.
egg
It's just
so.
It's just like,
Yeah.
whoa, that is so cool.
Totally.
Oh, you know what?
I went to Mexico once.
We can go there. It's probably kidding.
I wonder where that is.
It's probably kidding.
All right, so the deal with the graph on there, you're supposed, the graph is supposed to be where you say where it is from the top to the bottom, but it's either on the bottom or floating. Hey guys, on the next page, so you're supposed to write this down and your conclusions and everything right here, okay? On the next page, you're supposed to graph where the egg was, but how about instead of doing that, because I really don't think this experiment is good for a graph, because we couldn't like measure, it wasn't like floating midway, it was either down or floating, right? It was either, or here. What I'd like to do on this blank area back, I'd like you to draw your egg in your beaker and talk about the salt going in and that kind of thing. But then on this page, you gotta have any conclusions. Does anybody know why the egg floated? Yes, you can take your goggles off.
Wait,
Salt has sodium. Chemical
Chemical
reaction.
reaction.
Salt has sodium. So
Why did it make
that's
the egg
why.
float?
What's the element thing for that? It's like
Na. Na.
How? It
It's
doesn't
for
have
natrium.
any
We're gonna make
The word
this
natrium
into that
means salt.
seed.
That makes no sense. My mind is
So look at, so y'all look like you have barely any salt on the bottom. You have a lot of salt on the
We
bottom.
have way
of
too much
yours.
salt on the bottom. Oh,
That's called a saturated solution or a supersaturated solution of salt.
Ours like yellow.
So I
Our
wonder what
whole
the difference is.
very
Maybe their egg is bigger.
is weird.
Or something. Or smaller. Okay, so what's happening here, y'all, is this is called buoyancy. Oh, that egg really wants to float, y'all. It is really wants to
No,
float.
poor egg.
Oh, look at his
I
Now
feel
that
bad
one, you
for
can
it.
maybe measure that. Is it falling now?
What paper and book experiment did we do?
It's just like
Dropping
staying
it
out
like
like.
with gravity, dropping
I
it.
know.
Why does
Ours
ours
is
dropping?
Yeah,
it's
Drop the book in the
dropping.
paper.
Ours is
Salted.
yellow.
Oh,
Like
yeah.
no, but like us. But like look at theirs. Look at theirs.
Oh,
They
yeah,
look
yeah,
at mine,
yeah.
and it's like.
So,
Yellow.
now we could almost graph that one back there.
Heavier.
It was up a certain level.
The hair messed us up. And the hair had some kind of.
So, on
had
your
to do with
experimental
the
page,
hair.
guys, y'all might wanna say,
Oh, it's floating. It's floating.
since we did not choose to stir it, then flop it.
Oh, so what do I
Finally, back to the back, we have a floating egg. How many, was it 20?
How many?
Eliana, how much?
21. We had 21.
21. We did have.
Stop counting.
Okay, I like ours.
They were 21 on this, at this table back
I think
there.
we're just gonna put 20 because.
I can't get it back in the salt.
If you think back, I am going to bar. You're doing your.
I think it's
Alright. Okay, hello.
floating because of buoyancy.
Yes.
Alright? The salt makes the water more dense. And because of that, the egg can rise in it.
Okay, can we
If you are in a saltwater lake,
does anything?
you will float in it, like the Dead Sea, for instance. David, what did you wanna do?
I wanna pour all this.
You can pour all the salt in. That is fine with me.
Yes.
Salt.
By the way, those are hard-boiled eggs.
They
Yep.
are?
I think I'm gonna take a moment, I'm gonna make some deviled eggs. I'm gonna make deviled avocado. Hey, hey, hey.
Get ocean water on it. Get ocean water on it.
were gonna what?
Get ocean water on it too.
I like avocado and stuff.
Get ocean water on it.
That was a big egg.
Nice double dog.
Oh, goodness.
Boil an egg with two yolks. Just yolks. Have you ever opened one with 8 carrots together? Yes.
It's so sad.
What are there What is that?
There's like 18 babies in there. You can get them all.
That's okay. You really feel that. That's cute.
I'm
gonna
I
get
know,
you.
you eat their kids.
Wow,
You're so messed up.
Oh, we have a rooster. He's so mean.
I wonder why he's
Yeah. All that work.
I need y'all to take your beakers and go dump them in the sink
It's still raw.
in the restroom, and then rinse your beakers out real well and bring them back, please. Put your goggles in the bowl that's by the door as you go, but bring your beakers back. You can rinse off the spoons and bring the spoons back too.
Why do we get them?
Okay.
Yeah, I thought
Do I need to do something? So that salt water can go right down the drain, no problem.
Hey, can I do it in the other room that's empty?
There is an empty room right there, a little nursery room. And just, as long as you can fit the beaker under the sink to rinse it. I think the big ones might have a problem.
Oh, so that's over. Any other?
And we're done, yeah. Ms. Gosford, this was a short class.
I didn't really much time to study this week, so if I kind of take it home and take it and come back.
I studied yesterday. I'm still worried that
Well, sometimes, what helps you study, it's called the study guide.
I did the study guide.
She's like, how
Okay,
dare you?
John, Mark, and David, are y'all making Eliana wash the beaker after all that? Are you okay with that, Eliana? You all right? Okay. I've been let her do any of the other experiment, now she gets to watch the beaker.
Yeah, I was trying to see if she wanted to do anything.
You need it for
What do we
any
do with the
classes
extra
today?
salt?
I can just get it out.
Oh.
Yeah, and it looks like
What do we do with the extra salt?